In permutations and combinations, we generally discuss questions such as find the number of relations from A to B, or number of functions, number of one-on functions, or maybe number of onto functions. Now here we want to discuss, or we want to derive a general formula for number of onto functions from a discrete set A to a discrete set B, where number of elements in set A is n and number of elements in set B is m. And clearly this n, it has to be less than or equal to n. Now in case, suppose m is greater than n. Now let us take an example. Say A, I have two elements A1 and A2, and suppose here the value of n is 2, and suppose n is greater than n. Suppose m is 3. Suppose I'll take this as B1, B2 and B3. Now for this function to exist from A to B, A1 must have an image. So maybe A1 has an image B1. A2, suppose it has an image B3. Now there will always be at least one element which will not have any pre-image. So in this case, it cannot be an onto function. So in this case, number of onto functions will simply be 0. So if n is greater than n, then in that case, simply I'll say number of onto functions will be simply 0. So we want to work out a general formula when this m is actually less than or equal to n. Now, one of the way of doing it is, first I'll find total number of functions. Total number of functions that can be defined from A to B. Now, in order to define total number of functions, what I need is, for this A1, there must be an image. So it can be either B1, B2 and Bn. So there are m choices, and out of these m choices, I'll just need to select any one choice of image for A1. So in how many ways can it be done? It can be done in m ways. Again for A2, there are m choices. Again m for A3, and then finally it will be again m for An. So if I look at all the choices for all the elements, then it comes to m to the power n. So total number of functions from A to B that can be defined as m to the power n, where n is number of elements in the set A and m is number of elements in this set B. Now we'll find out total number of into functions from A to B. Now how do we work out number of into functions from A to B? Now for that we have to look into the definition of into function. A function is an into function if at least one the element in set B doesn't have a pre-image. So that means I'll have this condition where at least one of this Bi doesn't have a pre-image. Now how do I find that? So I'll say I need to find number of functions defined from A to B so that at least one of B1, B2, B3 or Bn, it should be missing. So here when I say B1, so it means the element B1 is missing. It doesn't have a pre-image. B2, element B2 doesn't have a pre-image. So at least one of these elements, it should not have a pre-image. Now we know that this formula can be generalized as summation nB1 minus summation nB1 intersection B2 plus summation nB1 intersection B2 intersection B3. So we can generalize this formula. Now how many functions can be defined from A to B so that B1 doesn't have a pre-image? So that is, how many functions can be defined from A to B so that B1 doesn't appear in the range? So each of these elements A1, A2 and An must find an image from B2 to Bm. So for A1, we have m minus 1 choices. For A2 again, I'll have m minus 1 choices. And for An again, I'll have m minus 1 choices. So the total number of functions that can be defined from A to B, which doesn't include B1, is simply m minus 1 to the power n. Now same is the case with B2. For B2 also, I'll get this n minus 1 c to the power n. For Bm also m minus 1 to the power n. So that is, I'll have the same condition for each of B1, B2 and Bn. So in order to find this summation, so in how many ways can I select single element? So it can be done in MC1 ways. So this summation nB1 is MC1 into m minus 1 to the power n. Now what about B1 intersection B2? So it simply means that B1 is missing and B2 is also missing. Now in this case, the total number of choices for A1 is simply m minus 2. For A2 also, it will be m minus 2. So it will be m minus 2 to the power n, because for each A1, A2 and An I have m minus 2 choices. And then now in how many ways can I select a combination of two elements? So it can be done in from m elements, I'll just need to select two elements, and that can be done in MC2 ways. For the third one, I think it should be plus MC3 m minus 3 to the power n, and this series will continue. So this is how we can find out total number of into functions from A to B. So I can find out number of onto functions as total number of functions, which is simply m to the power n, and then minus total number of into functions, which is minus mc1 m minus 1 to the power n minus mc2 m minus 2 to the power n plus mc3 m minus 3 to the power n, and will continue. So I can in fact write it as n to the power n minus mc1 m minus 1 to the power n plus mc2 m minus 2 to the power n minus mc3 m minus 3 to the power n. So I can write it as mc0, mc1, mc2. So it will be mcr and then minus 1 to the power r. So when r is even, it should be plus, and when r is odd, it should be minus, and then it should be m minus r to the power n, where this value of r varies from 0 to m minus 1. The number of onto functions that can be defined from set A to set B, where A has n elements and B has m elements, is given by this formula, which is summation r varies from 0 to m minus 1, mcr minus 1 to the power r, m minus r to the power n. So let us take up an example. Suppose I have to find number of onto functions defined from set A to B, so that number of elements in set A is 4 and number of elements in set B is 2. So in this case, the value of n is 4 and the value of m is 2. So clearly n is greater than m, so I can use the formula. Now the formula is number of onto functions is given as summation r varies from 0 to m minus 1, and m minus 1 in this case will be simply 1, and there will be m, so which is 2cr minus 1 to the power r, and which is 2 minus r to the power n, and n in this case is 4. Now if I'll put r as 0, I'll get 2c0 minus 1 to the power 0, 2 minus 0 to the power 4, and then plus 2c1 minus 1 to the power 1, and will be 2 minus 1 to the power 4. So here it will be 2 to the power 4, which is 16, and then it will be minus 2c1. So there will be 16 minus 2, that is 14. So number of onto functions from set A to set B, when number of elements in set A is 4 and number of elements in set B is 2, is simply 14. Now the question still remains, why are we discussing this formula here in binomial theorem and not in maybe functions or permutations and combinations? So it was actually in one of the test papers given to the students that I find a problem in binomial series which was related to number of onto functions, and I was quite surprised, actually happy to find that question there. So then I thought, okay, that's a good one. So next time when I'm going to teach binomial theorem, so I'll include number of onto functions formula then and there itself. So the problem was similar to this one, which was 10c0 10 to the power 5 minus 10c1 9 to the power 5, 10c2 8 to the power 5, and 10c9 into 1 to the power 5. So if I'm going to write it in summation form, I can actually write it as summation r varies from 0 to 9, and then it is 10c0 10c1. So there will be 10cr minus 1 to the power r, and then it is 10 9 8. So simply it will be 10 minus r to the power 5. Now if I'll compare it with this formula, so this is r varies from 0 to 9, which is m minus 1, and then it should be m and m here. So clearly I can say this formula is related to formula of number of onto functions. So here the value of m is 10. Now if I look at this value of n, what is the value of n here? The value of n is 5. So that is, I need to find number of onto functions from set A to set B, so that number of elements in set A is 5 and number of elements in set B is 10. Now we clearly know that when number of elements in B is greater than number of elements in set A, in that case the total number of onto functions is going to be simply 0. So in this case, number of onto functions will be simply 0. So answer to this question simply should be 0. And that is the reason we are studying this formula here in binomial theorem. Now in binomial, we'll study something again which is related to calculus, and which is Leibniz formula for successive differentiation, and it is also called as Newton-Leibniz formula for successive differentiation. Now we know product rule in differentiation, right? So if I have to differentiate u and v, so its derivative will be u v dash plus v u dash. Now if I differentiate it again, so then first derivative will be u v dash plus v u dash, and if I'll try and differentiate it again, I'll get this result, which is u v double dash plus 2 u dash v dash plus v u double dash. And if I'm going to differentiate it one more time, I'll end up getting this result, which is u v triple dash plus 3 u dash v double dash, 3 u double dash v dash, and then v u triple dash. So if I look at these three results, then if I look at the coefficients here, right? So here it is 1c0 and 1c1. Both of them, they are 1, right? 2c0 is 1, 2c1 is 2, 2c2 is 1, 3c0, 3c1, 3c2, and then 3c3. So these coefficients that appear in the result, they are related to binomial coefficients. So if we'll generalize this formula, so the general form for this formula will be, so if I have to find nth derivative of u and v, so here when I'm writing this part, it actually means its nth derivative. So nth derivative of u into v is nc0 u to the power n v to the power 0, nc1 u to the power n minus 1 v to the power 1, nc2 u to the power of n minus 2 v square, and then nCr u to the power n minus r into v to the power r, and this series will continue up to nCn u to the power 0 and v to the power n. So if we have to find nth derivative of this product u into v, then it is given as nc0, nth derivative of u, and 0th derivative of v. So when I say 0th derivative of v, it simply means the function itself. So nc1, now I'm going to differentiate u n minus 1 times, and then I'll differentiate this v 1 time. nc2, differentiate u n minus 2 times and differentiate v twice. And then finally nCn, so keep u same, u to the power 0 is 0th derivative, and 0th derivative is u itself, and this is nth derivative of v. So this is your formula for successive differentiation in binomial theorem. So I can write this formula as, so if I have to find nth derivative of u into v, then this formula can be written as summation r varies from 0 to n, nCr u to the power of n minus r and v to the power of r, where these powers, they are not powers of this function, they are derivative of these given functions. Now this Leibniz formula for successive differentiation can be proved using induction in the same way that we have done with binomial theorem. So we'll straight away take up a question, and the question is, find the fifth derivative of the function y equals x cube plus 2x square plus 3x into e to the power x. So actually I'll write it as y equals e to the power x into x cube plus 2x square plus 3x, and I'll take this e to the power x as u, and I'll take this function as v. Now u to the power 0 is actually its 0th derivative, which is same as e to the power x. Its first derivative, it will again be e to the power x, second derivative e to the power x. So for this function u, all the derivatives from 0 to 5 will be e to the power x. Now what about this v? Now this v to the power 0 is same function, which is x cube plus 2x square plus 3x Now its first derivative will be 3x square plus 4x plus 3. Second derivative 6x plus 4. Third derivative will be simply 6. Fourth derivative and its fifth derivative will be simply 0. Now I can use Leibniz formula for successive differentiation. So its fifth order derivative will simply be 5c0. Now fifth derivative e to the power x. So it will be e to the power x into 0th derivative of v. So there will be x cube plus 2x square plus 3x and then plus 5c1 e to the power x, and then first derivative 3x square plus 4x plus 3 plus 5c2. Now third derivative again e to the power x, and here it will be 6x plus 4. Next one will be 5c3 e to the power x into 6, and remaining two terms will be simply 0. So what I'll do is I'll take this e to the power x common. So if I take this e to the power x common, I'll get 5c0, which is 1. So it will be x cubed plus 2x square plus 3x and then plus 5 into, now 5c1 is 5 and there will be 3x square plus 4x plus 3. 5c2 is 10. So 10 into 6x plus 4. 5c3 is again 10, which is 10 into 6. So if I'll simplify, so fifth derivative of this function will be e to the power x, and then will be x cubed plus, so it will be 2 and then 15. So that should be 17x square, then 23 and 16. So that should be 83x, and then 15 plus 40 plus 60. So that should be 115. So the fifth derivative of this function, which is y equals x cube plus 2x square plus 3x into e to the power x, will be e to the power x into x cube plus 17x square plus 83x plus 115 using Leibniz formula for successive differentiation. Let us take another question, and which is find the nth derivative of y equals cos x into x square. So I need to find its nth derivative. So I'll assume this function cos x as my u and this x square as v, and I'll use Leibniz formula for successive differentiation. So I know that its nth derivative formula, so dny upon dx to the power n, is given by nc0, nth derivative of cos x, and 0th derivative of x square plus nc1, n minus 1th derivative of cos x, and then first derivative of x square, n minus 2th derivative of cos x, and second derivative of x square, and hereafter it will go up to nCn, and then 0th derivative of cos x, and then nth derivative of x square. Now we know that nth derivative of cos x function is cos n pi by 2 plus x. Now right, nc0 is 1. Now this is not cos x to the power n, it is nth derivative of cos x. So it will be cos n pi by 2 plus x, and it is not x squared to the power 0, it is 0th derivative of this function. Now 0th derivative of any function is that function itself. So here it will be simply x square. Now nc1 will be simply n. Now n minus 1th derivative of cos x will be cos n minus 1 pi by 2 plus x, and then derivative of x square, first derivative 2x plus nc2 is n minus 1 by 2 cos n minus 2 pi by 2 plus x, and then derivative of 2x will be simply 2, and hereafter all the successive derivatives of this 2 will be simply 0. So all other terms will be simply 0. So I can simply write it as x square into cos n pi by 2 plus x plus twice n into x, and will be cos n minus 1 pi by 2 plus x, and then 2 and 2 here will cancel, so I'll write n minus 1, and here it will be cos n minus 2 pi by 2 plus x. So the nth derivative of this function will be this result. Now we'll come to the proof of binomial theorem. So we need to prove binomial theorem for positive integral index, and we'll use mathematical induction. So suppose our statement Pn is a plus b to the power n is nc0 e to the power n b to the power 0, nc1 e to the power n minus 1 b to the power 1, ncn e to the power 0 and b to the power n. So the first step is I need to prove that P1 is true. So I'll find P1. Now P1 is a plus b to the power 1. So P1 will be 1c0 a to the power 1 b to the power 0 plus 1c1 a to the power 0 and b to the power 1. Now 1c0 is simply 1 and b to the power 0 is 1. So it will be a, and 1c1 is again 1. So this is a plus b. So a plus b to the power 1 is a plus b. So that is P1 is true. Now for the second step, I will let Pn be true. So I'll simply assume that a plus b to the power n, it is nc0 a to the power n b to the power 0, nc1 a to the power n minus 1 b to the power 1, nc2 a to the power n minus 2 into b square, ncr a to the power n minus r b to the power r, and plus ncn a to the power 0 and b to the power n. Now the third and crucial step is, using this second step, I need to prove that Pn plus 1 will be true. So I like Pn plus 1, and Pn plus 1 will be a plus b to the power n plus 1. So I write a plus b to the power n plus 1 as a plus b into a plus b to the power n. So now I'll put the value of a plus b to the power n from Pn. So I can write it as, so I'll write it as a plus b into, now it is nc0 a to the power n into b to the power 0, nc1 a to the power n minus 1 into b to the power 1, and then I'll write two terms here. I'll write nc r minus 1 a to the power n minus r minus 1 plus 1 into b to the power r minus 1, and then plus ncr a to the power n minus r into b to the power r, and then finally ncn into a to the power 0 b to the power n. So I need to multiply this a plus b with each and every expression. So now what I'll do is, I'll take the general case. I won't multiply it with all the expressions. So I'll multiply this a with ncr, and I'll multiply this b with nc r minus 1. So there'll be lot many terms. So if I'll multiply b with it, so I'll write nc r minus 1 a to the power n minus r plus 1 into b to the power r. And if I'll multiply a with ncr, I can write it as ncr a to the power n minus r plus 1 into b to the power r, and then there will be many other terms. Now in this case, what I see is this a to the power n minus r plus 1 b to the power r, it is same, so I can take it common. So I can write it as ncr minus 1 plus ncr, and it is a n plus 1 minus r into b to the power r. Now we'll use the property n is same, r differs by 1. I can write it as plus n plus 1 cr, and it is a n plus 1 minus r into b to the power r, which is the general term for Pn plus 1. For Pn, general term is ncr a to the power n minus r b to the power r, and for Pn plus 1, general term will be n plus 1 cr a to the power n plus 1 minus r into b to the power r. So therefore Pn plus 1 is true. So if P1 is true, and if we assume Pn is true, then from that we can prove Pn plus 1 is also true. So using mathematical induction, we can say that the binomial expansion of a plus b to the power n is either the summation r varies from 0 to n, ncr a to the power n minus r into b to the power r, or simply nc0 a to the power n b to the power 0, nc1 a to the power n minus 1b, ncr a to the power n minus r b to the power r, or ncn a to the power 0 n b to the power n. Now here the question is, we need to prove n to the power 7 upon 7 plus n to the power 5 upon 5 plus 2n cube upon 3 minus n upon 105 is an integer for every positive integer n. So we'll prove this result using mathematical induction. So the first step is, we need to prove P1 is true. So if we'll take n as 1, we'll write 1 upon 7 plus 1 upon 5 plus 2 upon 3 minus 1 upon 105. So here will be 105 15 plus 21 plus 35 into 2 and then minus 1. So there'll be 70 plus 20, 90 plus 15, 105. So it'll be 105 divided by 105, which is 1, which is an integer. So that means P1 is true. Now the second step is, we'll let Pk be true. So let Pk be true. So that means k to the power 7 upon 7 plus k to the power 5 upon 5 plus 2 k cube upon 3 minus k upon 105, and it is an integer. Now using this result, we need to prove that Pk plus 1 is true. Now for Pk plus 1, we'll write this expression as 1 plus k to the power 7 upon 7 plus 1 plus k to the power 5 upon 5 plus 2 upon 3 1 plus k to the power 3 minus k plus 1 upon 105. Now we can write this expansion as 1 plus, this is 7c1 into k, 7c2 into k square, and 7c7 into k to the power 7 whole divided by 7 plus, now this is 1 plus 5c1 into k, 5c2 into k square plus 5c5 into k to the power 5 whole divided by 5 plus 2 by 3, and this is 3c0, which is 1, plus 3c1 into k, 3c2 into k square, 3c3 into k cube, and then minus k plus 1 upon 105. Now in each of the expressions, this 7c1, 7c2 and up to 7c6, they are all divisible by 7. So it will be an integer. In the same way, for this one, 5c1 up to 5c4, they'll be divisible by 5. And the same way, 3c1 and 3c2, they'll also be divisible by 3. So that means all these three expressions, they are integers. So that means we'll get some integer, say m, and then plus, what I'm left with is 1 plus k to the power 7 upon 7 plus 1 plus k to the power 5 upon 5 plus 2 upon 3, 1 plus k cube, and then minus k plus 1 upon 105. So we can write it as m, and then this 1 upon 7, 1 upon 5, 2 by 3 minus 1 by 5, it is nothing but p1, and then plus, now k to the power 7 upon 7 plus k to the power 5 upon 5 and minus k upon 105, it is pk. Now we know p1, it is an integer, pk is also an integer, and this result is also an integer. So that means pk plus 1 is also an integer. So p1 is true. And if we'll assume pk be true, then pk plus 1 is also true. Then from principle of mathematical induction, we can say that this expression n to the power 7 upon 7 plus n to the power 5 upon 5 plus 2n cube upon 3 minus n upon 105 will be an integer for every positive integer n. Now here the question is, let p greater than or equal to 3 be an integer and alpha beta be the roots of this equation. Using mathematical induction, show that alpha to the power n plus beta to the power n is an integer and it is not divisible by p. So we can write sum of roots. So we know alpha plus beta will be p plus 1 and alpha into beta it will be 1. Now we need to prove alpha to the power n plus beta to the power n is an integer using mathematical induction. So first we'll prove p1 is true. So for p1 we know that it will be alpha plus beta and alpha plus beta is simply p plus 1. Now p is an integer, so p plus 1 is also an integer, so that means p1 is true. Now secondly we'll assume let pn be true, so that means alpha to the power n plus beta to the power n, it is an integer. Now using pn we'll need to prove pn plus 1 is true. So what we'll do is we'll multiply pn and p1, so we'll write alpha plus beta into alpha to the power n plus beta to the power n, so it will be alpha to the power n plus 1, beta to the power n plus 1, and then it will be alpha beta n plus beta alpha n. So we can write pn p1 and this is pn plus 1, and if we'll take alpha beta common, here we'll get beta to the power minus 1 and then plus alpha to the power n minus 1, so which is pn minus 1, and alpha into beta it is simply 1. So we can write pn plus 1 as pn into p1 minus pn minus 1. Now pn is an integer, p1 is an integer, and pn minus 1 is an integer. So from here we'll say this pn plus 1, it is also an integer. So that means alpha to the power n plus beta to the power n will always be an integer using mathematical induction. Now we'll come to its second part. That is, we'll need to prove that it is not divisible by p. Now for the second part, what I'll do is I'll write beta as 1 upon alpha and I'll write pn as alpha to the power n plus, instead of beta I'll write 1 upon alpha to the power n. Now we'll write p1 simply will be alpha plus 1 upon alpha, and which is simply p plus 1, and p plus 1 is not divisible by p. So we'll divide it with p, we'll get this remainder of 1 as 1. Now we'll find p2, we'll write alpha square plus 1 upon alpha square, so that should be alpha plus 1 upon alpha whole square and then minus 2, so it should be p plus 1 square minus 2, and in this case remainder will be simply minus 1. p3 will be alpha cube plus 1 upon alpha cube, and that should be alpha plus 1 upon alpha whole cube minus 3 alpha plus 1 upon alpha. So here it should be p plus 1 cube minus 3, and then alpha plus 1 upon alpha will be simply p plus 1, so it will be p cube plus 1 plus 3p plus 3p square minus 3p and then minus p. So now in this case we'll have all the expressions which are divisible by p and then minus 2. So in this case remainder when the value of n is 3 is simply minus 2. Now we'll find P4. P4 in this case will be alpha to the power 4 plus 1 upon alpha to the power 4, and then it'll be P3 into P1 minus P2. So what's P3? P3 in this case is P cube plus 3P square minus 2, and P1 is P plus 1, and then minus P2. P2 in this case is P square plus 2P minus 1. So here the constant term will be minus 2 and then plus 1. So it will be simply minus 1. If we'll continue the pattern, then we can write remainder of any power n will be R n minus 1 minus R n minus 2. So minus 2 is minus 1 and minus 1. Minus 1 is minus 2 plus 1. So in this way, we can write all the remainders for this given expression. We can show that these remainders, they'll be 1, minus 1, minus 2. So it can never be 0. So we can simply say this expression alpha to the power n plus beta to the power n is not divisible by p. Now another question is, using induction or otherwise, prove that for any non-negative integers m, n, r and k, where the summation varies from 0 to k, n minus m, r plus m factorial upon m factorial is equal to r plus k plus 1 factorial upon factorial k, and this is n r plus 1 minus k r plus 2. So what we'll do is, we'll let pk equals this summation m varies from 0 to k, n minus m, r plus m factorial upon m factorial, and this is r plus k plus 1 factorial upon k factorial, and this is n upon r plus 1 minus k upon r plus 2. Now we'll prove this result using induction. So first we'll prove P1 is true. So I'll put k as 1. So if I'll put k as 1, I'll get this summation as summation m varies from 0 to 1, n minus m, r plus m factorial upon factorial m, and this is factorial r plus 2 upon factorial 1, and this is n upon r plus 1 minus 1 upon r plus 2. So now I'll put the value of m as 0. So if I'll put m as 0, I'll get n into factorial r upon factorial 0, and then plus n minus 1 into factorial r plus 1 upon factorial 1, and this should be equal to factorial r plus 2, and here I'll take r plus 1 and r plus 2 as LCM. Then I can write nr plus 2n minus r minus 1. So here I'll write n into factorial r and then plus n minus 1, and I can write r plus 1 as r plus 1 into factorial r. Now here I write r plus 2 factorial upon r plus 1 r plus 2. I'll take this r together, so it'll be n minus 1 into r and plus 2n minus 1. So now here I'll take factorial r common. So if I'll take factorial r common, I'll get n plus n r plus 1 minus r minus 1, and here I can cancel r plus 1 r plus 2 with factorial r plus 2, so I'll get factorial r, and here it will be n minus 1 into r plus 2n minus 1. So I can rearrange this right hand side. If
I'll take r common, I'll write n minus 1 into r, and then we'll have 2n minus 1. And this is factorial r, and this is n minus 1 into r plus 2n minus 1. So left hand side is equal to right hand side. So that means P1 is true. Now the second step is we'll let Pk be true. So that means we'll let Pk be true. So that means simply summation m varies from 0 to k n minus m r plus m factorial upon m factorial, and this is equal to r plus k plus 1 factorial upon k factorial, and this is into n upon r plus 1 minus k upon r plus 2. Now using Pk, we need to prove Pk plus 1 is true. Now we can write Pk plus 1 as summation m varies from 0 to k plus 1 n minus m r plus m factorial upon m factorial, which we can also write it as summation m varies from 0 to k n minus m r plus m factorial upon m factorial, and then plus when the value of m is k plus 1. So here it will be n minus k minus 1 into r plus k plus 1 factorial upon k plus 1 factorial. Now we know that this summation m varies from 0 to k is equal to this right hand side. So we can write it as r plus k plus 1 factorial upon factorial k n upon r plus 1 minus k upon r plus 2, and then plus n minus k minus 1 into r plus k plus 1 factorial upon k plus 1 factorial. Now what we'll do is we'll take this r plus k plus 1 factorial common, and we'll also take factorial k plus 1 common. So we'll do that. We can write it as r plus k plus 1 factorial upon factorial k plus 1, and since we are taking factorial k plus 1 common, so here I'll need to multiply and divide it with k plus 1. So now I'll get k plus 1 into n upon r plus 1 minus k upon r plus 2, and then plus n minus k plus 1. Now we'll take this n together and we'll take k plus 1 together. So we can write it as r plus k plus 1 factorial upon k plus 1 factorial, and here if I'll take n common, I'll write k plus 1 r plus 1 plus 1, and then here I'll write minus, I'll take minus k plus 1 common, and then I'll get k upon r plus 2 and then plus 1. So this is r plus k plus 1 factorial upon k plus 1 factorial, and here will be n, and this is k plus r plus 2 upon r plus 1, and then minus k plus 1, and here will be k plus r plus 2 upon r plus 2. Now we'll take k plus r plus 2 common. So we'll take k plus r plus 2 common, and if we'll multiply it with r plus k plus 1 factorial, we can write it as r plus k plus 2 factorial upon k plus 1 factorial, and here we'll get n upon r plus 1 and minus k plus 1 upon r plus 2, and that is r plus k plus 2 upon k plus 1, and this is k plus 1. So that means p k plus 1 is also true. So using mathematical induction, we can say this result is correct.
Though we study binomial distribution in great detail in probability, we'll just make a reference to it here, and we'll try and understand when exactly a random experiment is going to follow a binomial distribution. So a random experiment will follow a binomial distribution if it satisfies the three given conditions. First, there should be n trials. That is, there should be something which should repeat n times. Or say, for example, suppose a coin is tossed 10 times. Or it could be we have simultaneous occurrences of n similar things. Maybe 10 coins are tossed simultaneously. So both these scenarios represent there are n trials. Now the second condition is trials are independent. Now one of the important conditions in binomial distribution is these trials or each successive or simultaneous trials, they should be independent of each other. Now suppose if I'm tossing a coin, now I get some result. Now if I toss the coin again, so the result that I'll get in case of a fair coin won't depend on what was the result in the previous case. So these trials, if they are independent, then we'll consider it for binomial distribution. And if they are not independent, then we cannot use binomial distribution. And the third one is, for each trial, there should be only two outcomes, either success or failure. So each trial must result in only two conditions or two mutually exclusive conditions. Either it should be successful or it should be a failure. So we call this probability of success as P, and we call probability of failure as Q. And we know that since it is mutually exclusive and exhaustive, so basically value of P plus Q should be 1. So binomial distribution is characterized by three conditions. So there should be n trials. The trials should be independent, and each trial should result in either success or failure. So binomial distribution is also represented as B and then n comma P, where this n, it represents number of trials, and this P, it represents probability of success. Now probability of failure can be worked out as 1 minus P. Now when n independent trials are conducted for any random experiment and we are looking for success and failure, so how many cases will be there, or what could be the value of random variable in these cases? So when I perform a trial n times, then the condition I can get is either out of these n trials, I get 0 success, like all the trials results in failure. Say for example, if I'm tossing a coin 10 times, suppose my success is getting a heads. Now out of these 10 times, I do not get heads even once. So it results in like all failure, which is 0 success. Or maybe if I'm tossing it and I get head once and the remaining 9 times it has resulted in tails. So in that case, it'll be only 1 success, or it could be 2 successes, or maximum it can result in 10 successes, that is, or n successes. So in the case of this coin experiment, so if I'm tossing a coin 10 times, then the minimum number of times I'll get heads is 0, and the maximum number of times that I'll get heads is simply 10. So this random variable here in case of binomial distribution, it takes the values from 0 to n. Now, probability of this random variable taking the value r, where this value of r lies between 0 to n, is given by, now when I say x equals r, it simply means probability of getting exactly r success. So that is, out of these n trials, r trials resulted in success, and remaining n minus r trials resulted in failure. So in this case, so if I say there are r successes, then, and these successes, they are independent, and we know that in case of independent events, probability of a1 intersection a2 is simply probability of a1 into probability of a2. So these r successes, I can present it as p into p into p, that is r times, and for each of this n minus r failures, I can represent it as q into q into q, n minus r times. Now we have multiplied this p into p into p r times and q into q into q n minus r times. Now I need to find out whether I need to multiply it with any coefficient or I should leave it just like that. Now I'll take up a simple case. Say for example, a coin, it is tossed maybe 3 times and I need to find the probability of x equal to 1, which is probability of getting exactly one success, and in this case I'll define a success as getting a heads. Now out of these 3 times I should have 1 heads and 2 tails. Now probability of getting 1 heads, it is 1 by 2, and probability of getting a tails, it is 1 by 2. So 1 by 2 into 1 by 2 will be 1 by 2 square. Now should I multiply it with any factor? Now when I'm tossing a coin 3 times, there could be the possibilities where either it will result in HTT or THT or TTNH. So all the 3 cases corresponds to exactly one success, but then there are distinct cases in sample space. So that is when I'm considering r successes, or when I'm considering in this case one success, I'll also need to find out where this success or which trial has actually resulted in this success. So basically it should have this number 3 multiplied to it. So it should be 3 into 1 by 2 into 1 by 2 square. So position, or we need to identify the trials where this success is going to come from. So that simply means how many different or distinct cases we will have in sample space where we'll have r of these trials, or of n trials, resulting in this condition where we'll have r successes and n minus r failures. So it means we need to select r distinct cases from n given trials. So it can be done in simply nCn-r ways. So I can express this probability of success as px to the x equals r as nCn-r. I write this q first, q to the power n minus r into p to the power r, and which corresponds to general term in binomial theorem. So that's the reason we call this distribution as binomial distribution. And here the value of r is going to start from 0 and end up to n. So that is the reason we call this as binomial distribution. And we also know that sum of all probabilities is equal to summation r varies from 0 to n, nCn-r q to the power n minus r into p to the power r will result in binomial distribution of p plus q to the power n, and the value of p plus q is simply 1. So that is sum of all these probabilities will always be 1. Now let us take another question in binomial distribution. Now the question is, a pair of fair dice is thrown independently 3 times. We need to find the probability of getting a sum of 9 on the upper faces exactly twice. Now the first thing that we need to figure out is whether or not we can apply binomial distribution to this random experiment. Now the first condition is condition of number of trials. Now a pair of fair dice is thrown 3 times. So that means the number of trials in this case is simply 3. So we have 3 trials. And secondly, it is already given the question that these trials are independent. So it's already given in the question. Now the third condition is each of these trials should result in a success or failure. So now in this case, getting the sum of 9 is success and not getting a sum of 9 is failure. So we'll have 2 cases. Either the sum on the upper faces is 9 or this sum is not equal to 9. So I need to find this probability of getting the sum 9 and the probability of not getting the sum 9. If I'll roll this pair of dice, I know the total number of elements in the sample space will be 6 into 6. So for each of the dice, I'll have 6 conditions. So 6 into 6, there will be 36 cases. So I need to figure out all those cases where the sum of the numbers is simply 9. So sum of the numbers will be 9 when we'll have this either 3, 6, 4, 5, 5, 4 and 6, 3. So if it results in either of these conditions, then the sum will be 9, else the sum won't be 9. So the probability of getting the sum 9 will be simply 4 by 36, which is 1 by 9, and not getting the sum 9, it is simply 1 minus 1 by 9, and that should be 8 by 9. Now it says we need to find the probability of getting exactly we need to find the probability of getting the sum of 9 exactly twice. So that is, out of these 3 trials, we need to find the probability of exactly 2 successes. So I'll need to find probability when the value of a random variable is 2. So it should be 3c2 q to the power 1 and p to the power 2. So it will be 3c2. What is the value of q? Q is 8 by 9. And what is the value of p? P is 1 by 9. So 3c2 is simply 3. This is 8. It will be simply 9 cube. So it will be 8. And this is 3 to the power 6. So it will be 3 to the power 5. So the probability of getting a sum of 9 on the upper face is exactly twice is 8 upon 3 to the power 5. So let us consider a case in binomial probability. And the question is, a multiple choice examination has 5 questions. Each question has 3 alternatives, of which exactly 1 is correct. We need to find the probability that a student will get 4 or more correct answers just by guessing. Now we need to figure out whether we can apply binomial distribution in this given question. Now the first condition is there should be n trials. Now if I look at this question, this multiple choice examination has 5 questions, and for each of the question the student has to guess an answer. So which makes it 5 independent trials, right? So this question, it will have 5 trials, and we'll assume that he's going to guess the options independently. So all these trials, they are independent. And the third one is, for each trial, there should be only 2 conditions, success or failure. In this case, we want to find out whether his answer is correct or his answer is wrong. So getting a correct answer is success in this case, and getting a wrong answer results in failure. Now what is the probability of getting a correct answer? So if any question has 3 alternatives, out of which exactly 1 is correct, then probability of getting the correct answer is 1 by 3. So that means probability of getting a wrong answer is 2 by 3. Now we need to find out of these 5 trials, a student will get 4 or more correct answers. So that is, we need to find out the condition where we have at least 4 successes. That is, the value of random variable should be either 4 or greater than 4. So I know that the value of r will lie between 0 and 5. So that is 0 success to 5 success. So probability of x greater than or equal to 4 simply will be probability of x equal to 4 plus probability of x equals 5. Now what is probability of x equal to 4? So that is 5c4 q to the power 1 p to the power 4 and plus 5c5 q to the power 0 and p to the power 5. So now I'll put the value. So I'll write it as 5c4, and what's q? Q in this case is 2 by 3, and p is 1 by 3 to the power 4, and then it'll be 5c5, it is 2 by 3 to the power 0, and then 1 by 3 to the power 5. So actually I'll take 1 by 3 to the power 5 common, and here I'll get 5c4, which is 5, 5 into 2 is 10, and then plus here will be 5c5, which is 1. So answer to this question will be 11 upon 3 to the power 5. So the probability that a student will get 4 or more correct answers just by guessing is simply 11 upon 3 to the power 5.
Now question number 17, it says, find the number of pair of integers x and y satisfying the equation xy x plus y plus 1, and this is 5 to the power 2018 and then plus 1. Now we'll consider left hand side and right hand side separately. So left hand side is xy into x plus y plus 1, and right hand side is 5 to the power 2018 and then plus 1. So we know that any power of 5 will end with 5 and then plus 1. So this right hand side will always be an even number. So this RHS, it is even, and we can also write this 5 as 4 plus 1 to the power 2018 plus 1. So here I can write it as, this is some multiple of 4 plus 1 then plus 1. So it is of the form 4k plus 2. So this right hand side will be even, but it is not divisible by 4. Now we'll come to left hand side. So now we know that right hand side is even. So this left hand side, it must also be an even number. So left hand side will be even when at least one of x or y is even. So suppose x is even, y is odd. Now if x is even and y is odd, so this x, it is even, y is odd, and then into, now this is even and then odd plus 1 is also even. So this number will also be an even number. So it is even into even. So it means this left hand side is divisible by 4. So 4 divides left hand side. Now when I have, suppose x is even and y is even. Suppose both the numbers they're even. So if both the numbers they're even, then x into y again will be divisible by 4. So for any possibility of x and y, this left hand side will always be divisible by 4 and this right hand side is not divisible by 4. So that means left hand side can never be equal to right hand side. So that means the number of pairs of integers satisfying the equation will be simply 0.
Now the question is, find the value of fractional part of 3 to the power 1001 divided by 82, where these brackets, they represent fractional part function. Now we need to find divisibility with 82, and we know that 3 to the power 4 is 81 and that is close to 82. So I can write it as 82 minus 1. So first what I'll do is I'll write this 3 to the power 1001 as 3 into 3 to the power 1000. And then I can also write it as 3 into 3 to the power of 4 to the power of 250. So I'll write this expression as 3 into 3 to the power 4 to the power 250 and then divide by 82. So that should be 3, and 3 to the power 4 is 81. So I'll write it as 82 minus 1 to the power 250 divided by 82. Now I'll use the shortcut. So I'll leave all the multiples of 82. I'll simply write it as 3 into minus 1 to the power 250 divided by 82. Now minus 1 to the power 250 is 1. So it'll be 3 by 82, which is a number which lies between 0 and 1. So between 0 and 1, fraction part of x is simply x. So answer to this question simply will be 3 by 82. So here the question is, we'll need to prove that 37 to the power n plus 2, 16 to the power n plus 1, and 30 to the power n is divisible by 7. So again, we'll use shortcut. So we have to express these numbers as some multiple of 7. So I can write 37 as 5 into 7 plus 2. I can write 16 as 2 into 7 plus 2. And I can write 30 as 4 into 7 plus 2. So I'll write 5 into 7 plus 2 to the power of n plus 2. 2 into 7 plus 2 to the power of n plus 1. And 4 into 7 plus 2 to the power of n. Now I'll use shortcut, so I'll discard all the terms which are multiple of 7. So then I'm left with 2 to the power of n plus 2, 2 to the power of n plus 1, and then 2 to the power of n. So if I'll take 2 to the power n common, so I'll get 2 square plus 2 plus 1, and it'll be 2 to the power n into 7, which again is a multiple of 7. Now question number 7, it says, let a, b, c be 3 natural numbers such that a square plus b square equals c square and c minus b is equal to 1. So we need to prove that first a is odd. Now we can write a square as c square minus b square, which is a square, and this is c plus b into c minus b. Now c minus b, it is 1. So we can write a square as c plus b. Now c minus b is 1, so which is an odd number. So if c minus b is an odd number, that means one of c and b is even and other one is odd.
So if we have one number even and other number odd, then the sum of even number and odd number is also an odd number. So a square is an odd number, and if a square is an odd integer, in that case a is also an odd integer. So that's your result number 1. Now in the second part, we'll need to prove that b is divisible by 4. So now we have two results. C minus b is equal to 1 and a square equals c plus b. Now what we'll do is we'll subtract this first from second. So it'll be minus 1 and it'll be minus c plus b. So we can write 2b, and this is a square minus 1. We'll write this b as a minus 1, a plus 1 upon 2. Now in the first part, we have already proved that this a is an odd number. So let us say a is some 2k plus 1. So we'll take a as some 2k plus 1. Then we can write this b as a minus 1, which will be 2k, and then a plus 1, which will be 2k plus 2 divided by 2. So now we can cancel this 2. We can write b as 2k into k plus 1. So b is a multiple of 2, and then it's a product of two consecutive integers, k and k plus 1. So out of these two, k and k plus 1, one of them must be an even number. From here we can say that b is divisible by 4. Now we'll come to its third part, and that is we'll need to prove that a to the power b plus b to the power a is divisible by c. So let us take a to the power b. Now we have already shown that this b is a multiple of 4. Then we can write this b as some 4m, and we can write it as a square to the power 2m. Now a square is c plus b and c minus b is 1. So we'll add them. Then we can write 2c equals a square plus 1, and we can write a square as 2c minus 1. So we'll write a square as 2c minus 1. Then we can write this as 2c minus 1 to the power 2m. Now we'll need to find divisibility by c, and the shortcut says express this a to the power b as some multiple of c, and then whatever is the constant term, that's your remainder. If a to the power b is divided by c, it leaves the remainder minus 1 to the power 2m, that is simply 1. Now we'll find b to the power a. Now we know that b is simply c minus 1, so it will be c minus 1 to the power a. Now again, if we'll use shortcut, we'll get this remainder as minus 1 to the power a. So if b to the power a is divided by c, then remainder will be minus 1 to the power a, and since a is an odd number, remainder is simply minus 1. Now we'll add a to the power b and b to the power a. Then this remainder is plus 1 and this remainder is minus 1, which will eventually cancel out. So that means a to the power b plus b to the power a is divisible by c. And this is how we solve these questions. Now question number 23, it says find the remainder when 29 to the power 29 to the power 29 is divided by 9. Now we'll use shortcut. So we'll express 29 as 27 plus 2. And 27 is 9 into 3, which is a multiple of 9. So 9 plus 3 into 2 to the power. So we can write this number as 9 into 3 plus 2 to the power 29 to the power 29. Now we need divisibility by 9. So we can leave this factor. Then its remainder will be 2 to the power 29 to the power 29. Now for the powers of 2, we need to find a number which is close to any multiple of 9. So we know that 2 to the power 6 is 64, which is 63 plus 1. So we can actually write this as 2 to the power 5 into 2 to the power 24, which is 2 to the power 6 to the power 3 to the power 29. So it will be 2 to the power. Now 29 into 5 is 145. So it will be 2 to the power 145, and 2 to the power 64 is actually 9 into 7 plus 1 to the power 29 into 3. Now again we'll need multiple of 9. So remainder is simply 1. So it will be 2 to the power of 145. Now again we can write 2 to the power 145 as 2 into 2 to the power of 144, which will be 2 to the power 6 to the power 24. Now 2 to the power 6 again is 9 into 7 plus 1 to the power 24. Again remainder is 1, which is multiplied with 2. So the remainder when 29 to the power 29 to the power 29 is divided by 9 is simply 2, and that's your option number B.
So let us take up another question, and the question is, if n is defined as factorial 1 plus factorial 2 plus factorial 3 up to factorial 100, then we need to find the value of fractional part of n by 5, where these brackets, they represent fractional part function. Now what I'll do is, I'll put the value of n, so I'll need to find fractional part of n by 5, and I'll write it as factorial 1 plus factorial 2 plus factorial 3, and it goes up to factorial 100 divided by 5. Now what I'll do is, I'll split it in two parts. So I'll write it as factorial 1 plus factorial 2 plus factorial 3 plus factorial 4 divided by 5, and plus factorial 5 plus factorial 6 plus factorial 100 divided by 5. Now for the second case, factorial 5, factorial 6, factorial 7, factorial 100, all of them, they'll have 5 inside, right? Because the product of first 5 numbers is the product of first 6 numbers. So 5 will get cancelled every time, and this expression is nothing but an integer. So this is an integer. And we know that fractional part of x plus k, where k is an integer, is simply fractional part of x. So what I'll do is, I can simply write it as, it is fractional part of factorial 1 plus factorial 2 plus factorial 3 plus factorial 4 divided by 5, and which is 1 plus 2 plus 6 plus 24 divided by 5, and which in this case is 33. When 33 is divided by 5, so this is 6 plus 3 by 5. Now its integral part is 6 and its fractional part is 3 by 5. So answer to this question is simply 3 by 5.
So this is nC10, and n plus 1 C10, we can write it as factorial n plus 1, factorial 10, and factorial n plus 9. I can also write it as nC10, and this is n plus 1 into factorial n, factorial 10, and this is n minus 9 into factorial n minus 10. Now factorial n upon factorial 10, factorial n minus 10 is nothing but nC10 again. So I can write this as nC10 into nC10 n plus 1 upon n minus 9. So we can write it as nC10 whole square into n plus 1 upon n minus 9. So now we can say that this product nC10 into n plus 1 C10 is equal to nC10 whole square into n plus 1 upon n minus 9. Now the product of binomial coefficients, it is an integer. N plus 1 upon n minus 9, it may be a fraction where the denominator part gets cancelled by nC10 square. So we cannot assume n plus 1 upon n minus 9 as some k square. If we'll assume it as k square where k is an integer, we won't get any solution, and that is not the answer to this question. So what we'll say is this n plus 1 upon n minus 9, it should be a perfect square of some rational number. So it should be of the form p square upon q square. Now we need to find the value of n so that I can express it in the form of p upon q whole square. Now another way of looking at the problem can be, we can write this as n plus 1 into n minus 9, and it should be p square into q square. So this product, it should also be a perfect square for same values of n. So if I'll multiply them, I'll write n square minus 8n minus 9, and this should be equals to some k square
where k is an integer. Now if I'll complete the perfect square, I'll write plus 16 and minus 16. So I'll get n minus 4 whole square minus 25 equals k square, or n minus 4 whole square equals 5 square plus k square. Now it forms Pythagorean triplet. Now the only Pythagorean triplet containing 5 is 13 square equals 5 square plus 12 square. So from here we can say the value of n minus 4 should be 13 and value of k should be 12. So here the value of n is simply 17. So the only value of n for which this expression nc10 into n plus 1 c10 is a perfect square is n equals 17. So if I'll take n equals 17, then this n plus 1 upon n minus 9 will be simply 18 upon 8, which is 9 by 4, which is 3 by 2 square. So it is a perfect square, but it is a perfect square of a rational number, which is not an integer. So answer to this question is number of integral values of n is simply 1. That's your option number B.